It's the tower problem. Antenna guy wire problem.
I gotta go over it some more. Something to walk over.
Hang on, let me see if it's that one or. Okay, no, sorry, it's the problems aren't the ones that were due on the 16th, it's the problems that are due tomorrow. Okay.
I didn't recognize those names of the problems
Yeah.
anyways.
That's the one that's due February 20th. Because if you look at it, one is so Ben, yours is the one where there's a door and there's propping up a thing on the door handle. Jordan, yours is they're using a lever to raise a rock. And then Armando, yours is a tower problem. It's a radio tower, and that's the stuff that's due on this is the second homework set. This is the due on the 20th. Let me just go in there and look at it, and I'll show you which one's which. Okay, course materials, week 5. It's not week 5. Yeah, this is one. Should be this one. Review. So there's that one. So if I go down here, did I split it up? Nope, that's the house. Let's go back. Oh, about an axis. Maybe it's this one. Yep, it's this one. So
Go to my rock problem.
I'll show you the, so one of them is this one. This is the homework assignment that we're playing with, because these are all couples. We've already covered all the material for them. So this one is the rock problem is number 7. That's the rock problem. So you're trying to move a force by applying it to the steel bar, and basically you're going to shift this force into different spots.
Okay.
Okay, that's where that one is. And then
Not too bad.
Ben's got number 11. That's the door. Okay, the door problem. Then Armando, you've got this one. That's the tower problem. And Ben, Armando, Jordan.
So know
what homework that is.
I'm showing him just a second. It's the couple's homework. So it's the couple's homework. So if I go back to Blackboard, it's this one right here. It's the couple's homework.
This makes me happy.
And just to let you guys know, I don't. How's the sound over there, Beverly? Because we're getting a downpour out here.
We can hear it, but it's
Okay.
not bad.
Okay. Because it's definitely coming down. All right, the other thing is there's a quiz, and this quiz is mostly over stuff we've already done and have been playing with and doing a bunch of. So there is a quiz, and it's due tomorrow. The couple's homework is that homework that the what will be presented
Hey,
Friday.
Sorry.
That's what happens when you get in, come in the rain. So this is problems to present in class from the homework, from the couple's homework.
Yeah.
All right, so the door problem, Ben, you've got that. The rock problem, Jordan's got it. Armando's got the tower problem, and Jasim has the tapping the hole problem. Okay, so let's go. So I promise, because this is one of my favorite problems, and this actually looks at simplifying forces and moving forces forces around, so it's still along the same types of stuff. Is we got a dirigible. Okay? We've got a dirigible. There it is. There's our dirigible. That's a blimp, a dirigible. Could be a zeppelin, depending on how you want to talk about it, right?
Never heard of dirigible.
Dirigible? You never heard of a dirigible?
Never.
Dirigible, zeppelin, blimp.
Dirigible. That sounds like,
German.
yeah. On my video game, they called them dirigibles.
They called them dirigibles in the 20s.
Yeah.
20s and 30s, they called them dirigibles. Zeppelins were primarily, specifically for the Germans. But we got a dirigible. Basically what we want to do, currently it's attached at point B, okay? And it's in equilibrium at point B. So we're saying if the dirigible is tethered by a cable attached to its cabinet B, if the tension is in the rope is 1040 newtons, replace the force exerted by the cable at B with an equivalent system done by two forces at A and C. Okay? So what we're going to do is instead of having this one cable, we're going to put two cables and we're going to have it with an equivalent force at A and C. So this is just using our information where we can slide things around, play with things, and have them go back and forth. So basically what I've got, so there's my picture. So I start by drawing the problem like this. So I've got A and C, and here's my B. Here's the force that's currently being applied. This is 60 degrees. Because I've got that at 60 degrees. I've got that at 60 degrees. Do I want that? No. This is going to be 30 degrees. Because that's got to be 60 degrees. All right? And I've got to do equivalent forces here at A. This is B at C. And the tension in this one is equal to 1040. All right? So, if I do my summation of the forces in the x direction, I've got to have the tension times the cosine of 60 degrees. And now this has got to be an alpha, and that is an alpha.
Wouldn't they all be 60 degrees?
These, we don't know. Because right now I've got to apply this force. I'm gonna move. This is going to be force AC. This is going to be force A, and it's got to be equivalent to this one right here. Okay. So if I do that, this is going to be force A sine alpha plus force B sine alpha. Now, the one thing I do know about these two forces is that they're going to have to be pulling in the same direction as this one is. I mean, they've got to be that way, otherwise I'm going to get a torque, right? They're going to have to be pulling in the same direction. So I'm going to use symmetry to help me out. That's why I know that those angles are both alpha. Summation of the forces in the y direction, that's going to be my T, and that's minus because I'm going down. Cosine of, I can either do cosine of 30 degrees or I can do the sine of, or the sine of 60 degrees. But if I'm going to go ahead and leave it in the cosine here. And I can also do this as T sine of 30 degrees. And you'll see why I want to do that in a minute. Okay?
I have a question. I think you explained it Friday. But normally when you're going in the y direction, you use sine. Why are we using cosine here?
Okay, if I do this, this is the angle that I have. This is 60 degrees.
Yeah.
That means this one has to be 30 degrees. This side is my T cosine 60 degrees. And that's gonna be my TX, right? This one is T sine 60 degrees on that side, okay? Now, that's right, 30 degrees, make sure I've got that. Yep, 30 degrees, yep. So I've got that, or this is equal to T sine 30 degrees, and this is also equal to T cosine 30 degrees. I can use either one.
Okay. So if you were gonna do it the other way, you'd do negative T sine 60.
This one,
No, for the
this one, yeah, if I'm doing it the other way, I'd do negative T, yeah, sine 60, yep.
Okay.
I could do it either way. You'll see why I want to use the cosine here in just a second,
Okay.
okay? Or use the sine here in just a second versus the cosine. Because it's going to simplify the math in just a little bit. And that gives me, and I got to do so I got negative force A cosine alpha minus force B cosine alpha. So my summation of my forces looks like that. And now you'll see why I want to go ahead and use the sine versus the cosine in this case. Because I can do this. So if I do this, I can have the sum of the forces in the x direction is going to equal T sine 30 degrees F A plus F B sine of alpha. So all I did was I'm going to use this form here, and I'm going to use that right there, and I factored out the sine. I'm going to do the sum of the forces in the y direction. It's going to be T minus T cosine 30 degrees is equal to minus FA plus FB cosine alpha. Okay, so I kept the cosine part here, and then I factored out over here. Now you see why I did that is because the way I've written it, what happens here is if I divide one by the other, I can do a simplification of my system really quickly, because I get the tangent of 30 degrees, and this is the negative tangent of 30 degrees, is equal to the negative sine alpha over cosine alpha, which is equal to the negative tangent of alpha. So alpha has to equal 30 degrees. So even though I move my forces, I'm splitting this force up, I end up with the same angle. I just showed that I split up and I got the same angle. Because this is what I did, there's our tension here, and then, so that angle has to be the same as the angle that I currently am at. So that, by doing it this way, it made it really quick and easy to prove that part. So I got that part, but now I still have to deal with my forces, right? Still got to deal with my forces. So the way to do this is now I'm going to use my moments. Okay? The way to do that part is I'm now going to use my moments. Okay? And I'm going to do a moment about C. So I'm going to come over here and I'm going to do the moment about C, and that's going to give me the force due to A. Okay? So my moment about C is going to give me my 1040 cosine of 30 degrees. And I'm going about C, so that's got to be 4. Minus FA cosine of 30 degrees. And now I have to go to the distance from C to A, which is 10.7. And that's all got to equal 0. So I get my 1040 times 4 times my cosine of 30 degrees is equal to 10.7 FA cosine of 30 degrees. So I'm going to take my 1040 times 4 cosine of 30 degrees divided by my 10.7 cosine of 30 degrees is equal to FA. FA gives me something that looks like 389. I'm going to do the next part. Now I'm going to do the moment about A. It's got to equal 0. This time it's going to be 1040 cosine 30 degrees. And now I've got to do 6.7 because I'm going from A, so it's going to be 6.7 minus F of C cosine 30 degrees. And now I'm still at 10.7. And when I solve for FC, I get 651.
So what do the distances look like, so I can write those down?
Yeah, and this actually is problem 383 in your book. It's 383 in your book. Do what?
Can you slide that out so I can see the bottom of that,
You want me to do that?
yeah.
Do what?
All meters or, yeah,
You got 651. Yeah, these are all in newtons.
So the moment just, it makes it easier because you can use distances.
Moment makes it easier to solve for the forces in this one. Because partially, here's why the moment makes it really easy to solve for. So the question is why use the moment? Well, the moment's here is because I can go about A and solve for F of C. And I can go about C and solve for F of A, and I've eliminated the variable completely.
I see.
Now, if I go back here, I could do the same thing up here. I've got 2 equations, 2 unknowns, but I'm not sure I have enough information to solve one for the other. Well, actually, I have 3 equations. Oh, well, here's the other problem. I have 3 unknowns in this equation. I solved and got rid of alpha, but now I only have, now I can solve that gives me this, but I need another independent equation to solve for the other ones, because I need to have 3 equations to have 3 unknowns.
I see.
So I've got to use one of these. Now, once I have this, I can plug that back into this. You know, the third one becomes really easy. You have your choice, whichever way you want to do it.
Okay.
But you do have a 4th one now that gives you a check.
Okay. Cool.
Okay? All right, so let's kind of look at the next kind of section. Huh? Got a question over there?
I was
No,
talking to Mike.
he said something.
Oh, okay. Just the way the sound came, it sounded like that somebody asked a question over Enid, because it's
Pretty weird sounding, huh?
It just was, just where the direction of the sound came from.
Mouthy Michael Mondays.
Okay, all right, so let's look at problems that look like this. Because the next set of homework, let's go in here. The next set of homework is gonna look at, we're gonna do a lot of bending. And the reason we're gonna start looking at these bending moments and playing with these bending moments is because eventually what we're gonna do, and eventually where we're gonna get to is this. Because we're gonna have a beam, and think about your trusses, okay? When we had our trusses, they were supported in here, so we had some sort of support, and then we applied a force there. Now structurally, we know that the material, and this is where you get strength of materials, we know that if I do this, I can have something that happens to the beam that looks like this, right? We get a beam that'll actually bow like that, because we do that all the time, right? I can make my stuff bow, and we can get that. So we're gonna end up with what we call shear stress, torsion, and bending. Okay, so we're gonna get bending, shear stress, and torsion, but what we're gonna have to do is we'll start looking at cutting our beams in an imaginary way in order to look at the forces on the beams. And so that's one of the reasons that we wanna start looking at those equivalent forces and those equivalent torques, because we're gonna start moving them away from the problems that we've been doing. And so we're gonna start looking at things that are happening on beams. So that's why we want to do these force coupled problems. We want to be able to say, well, what are our forces that we have? What are the various things that we want to do? The other thing that you'll see here is, this is on rollers, so I can shift it around potentially. This is a fixed point, but I'm actually looking at this problem, and I can do a variety of different things. So when we were in physics and started looking at physics, we said, all right, let's look at this problem here. So I have my problem. I've got my bar, and I've got something that's attached here and something that's attached here, and I've got this end, and I've got one going down, I got one going up, and I got one going down. One of the questions that we might have had, and this is 150, this is 600, this is 100, this is 250. One of the problems we may have had is, well, what are the forces on those two objects there? Well, that's going to be, we can do some of the forces real quick. I can do some of the forces, and this is force A, and this is force B, and now I've got 150 going up, I have 600 going down, I have 100 going up, I have 250 going down, and then I have force A going up, and I have force B going up. And so now if I add all those numbers together, I get 150, 250, that subtracts, I get a negative 600 going down, plus FA plus FB. I can't solve for FA and FB because I've only got one equation. Well, now I do my torques, right? So I can do my torques, and so now I can do the force R on FA. So do it about FA, so this one's going to be about, I do the sum of the moments is equal to 0, and I do it at A, then I would do this distance over here, and I would do the distances, and I could find FA or FB, depending on which one I'm setting up. But now if I want to ultimately get to this situation, I've got to start playing with these equivalent force couple systems. And so the couple is part of the sum of the moments of each force, and once you find the point, you can transfer it around any other point. Because I want to be able to do some methodology. So I want to be able to actually do this. So if I do it, I can look at A and B. I don't necessarily have to look at my fixed points. I can do it about A and B. So let's kind of look at that. So if I could compute the resultant force at couple A, so now I've got, there's my 150 in the J. Got a question?
Oh, no,
Okay.
I'm sorry.
It's all right. I got my 150 in the J, positive. I've got a negative here, positive there, negative there. And now I go back to the original problem and I look at the distances. Okay, so if I'm looking at A, this is 106, or 1.6 this direction, 2.8 that direction, 4.8 there. And that's just adding up these numbers to get those distances. That's all that is. So now I can do that. There's my resultant force, which is what we already did, right? We already looked at my force in the y's. And now I can look at my moment around this spot, and I want you to look at how they actually draw the picture, okay? So if I have an equivalent for 600 newtons that is going down, but if I do this, which way is my torque going? My torque is going, I'm pushing down this way, so my torque is curling this way, and it's because it's going clockwise, it's negative. So basically all I did was, or all our author did, was add up my forces, so I know which way I'm going, and we're applying it all at force A. Now I can do the same thing to do it at force B, okay? We still know that the torque, or we still know the force is 600 newtons. I can move it over to force B. But now I want to do, looking at the other part, and that gives me this part here. I can do it a couple of different ways. I can incorporate it and bring it in, and I can have it come down.
Where are they getting that 2880 and 1000?
The 2880 is coming from 4.8 times 600.
Oh.
2880, this is the part that we already had over here. And now, if I look at it, there's my 2880. The difference between those two gives me 1000.
I see.
You could have done it the other way too. I mean, this goes back to how many times have we done them in different directions right now, and it's just because of which way the problem, which way it makes it simpler. And he's showing you a different way to do it right now. So now, and the reason he's doing that is because now you can get to this spot, and you can go, okay, I can tell you wherever this is, solving for whatever my x is for my equivalent force, that if I want it equal to this, how far away do I have to be? Where do I have to put this? Where do I have to put this roller? Where do I have to put this roller so this doesn't move? Okay? So this one really is just kind of taking it into account and working the different problems. So, because now what's going to happen is you're going to get this. So, I've got this is that one, yeah. I've got this one. I got a 3-meter beam that's shown like that. And it's determine the loading of the problem that is equivalent to this. So there's my 3-meter beam. And here is a bunch of those beams. And you got to find out which one of these are the equivalent. So which one's having an equivalent loading?
C.
C?
I can't tell, I can't see the top one.
Well, you can see the top one. There's the top one right there.
Dun, dun, boom, boom.
Well, now let's look at the first part of this problem, okay? Some of these you can do really, really quick, because what's the net force on this problem? What's the net force being applied?
-500.
Negative 500. So let's go down here. So I can, if I look at this, I can get rid of B right away, because that's positive 500. I'm not loading that one with a positive 500. So right now A is okay because I've got a positive 500 or negative 500. I got a negative 500 here. I got a negative 500 there. That's okay.
I think it's the one in the middle, the third one on the second row.
Third one in the second row.
Yep. That's the guess.
Let's see which one.
Because they're just doubling
They're just
torque on
doubling.
each side, but the force is still the same.
No,
It's
not
not
that.
that.
No, it's not that
It's
one.
gotta be the one that's, I would say it's the one that has 4, there's 200 times 500 that's 1,000, and then the other one's 600, so there's 400 left over.
Oh, I didn't see that. 300 newtons.
So there's 400, but it's in the, so that'd be,
This is 800, so,
I didn't see
so,
the 300.
so all of them have a net force of 500. All of them have a net force of 500, but they're not all in the negative direction, okay? A is in the negative direction, B is in the positive direction, C is in the negative direction, D is in the negative direction, this one is in the negative direction, this one's in the negative direction, this one is also in the negative direction, and this one's in the negative. So we got rid of one of them just by going through there.
So it could be H.
it could be H or E.
I was thinking H.
I'm thinking H and E? Okay.
Thinking G could be a possibility. It's got 800 down, 300 up, 500.
I thought this was the one you started with.
It was.
Okay, that's the one you started with.
But I think it's 800.
Okay, so the one we know that we're looking for, has 500 newtons going down. And now if I do this, so I'm gonna do the moment here. This is 3 meters long. We want a moment about A. So my sum of my moments about A, all right, some of the moments about A are, I'm gonna get my 500 that's in the positive direction, and it's 500 newton meters times 200 minus 300 at 3 meters.
Which one are you doing?
This is the original. This is my 200.
Oh.
This is my 200. This is my 500. And this is my 300. And this is my 3 meters.
So what are the little side, the Mindy arrows, what are those?
These are torques.
Okay,
This is going like this, or going like this.
okay.
Could you zoom out a little bit?
The beam is loaded as shown. Determine the loading of one of these that are equivalent to each one. So this gives me 1,000 minus 900. Is that right? Something's not.
1,000 minus 600, wouldn't it?
3 times 3 is 9.
Is it talking about the torques though? Because the torque on that one was 200. Or, yeah, the torque up is 200.
This torque's up to 200.
Yeah. So would you take 300 times 200?
This torque is going down here. My loading is there. 500 newton meters. Oh, yeah. Well, something's not right. Okay, so I have my 500 newton meters plus my 200 newton meters. Now, minus my 300 applied at 3. Because there's 500 at this end, 200 at this end, those are additive. And now I'm doing it about A, and I've got my 3 times my 3 there. So now I get my 700 newton meters
Minus 900.
minus 900 newton meters. Just a second. Minus 900 newton meters gives me my 200 newton meters. So now I gotta figure out which one gives me 200 newton meters down here. So if I do this, if I do that one around, let's do. This one is, I only have 400.
See, English is 200.
Oh, well, this one's this one. Look at F. So if I get some of the moments at A for F, this one's for F, I get my 400 Newton meters minus 200 times 3. It gives me make sure that's right. 200 that way. 200. This one should be 200 that way. This gives me 400 Newton meters minus 600 Newton meters. And that's going to give me my 200. And this one's going that way. This one gives me negative. My 400. Yep, this one's telling me it's going that way. But this one is, oh, this one's also going that way. It's negative 200. We clean it up. It's Monday,
And it's raining.
and it's raining, and
Which is a good thing.
which is a very good thing. So I've got 200 here, 300 here. I've got my negative 500, or my positive 500 there, my negative 200 there. So I can do this as a negative 200 Newton meter, or positive, yeah, no, these are both going the same direction, so they're additive. 200, 300. So if I do the sum of the moments, this is Newton meters, so this is 500 Newton meters plus 200 Newton meters. And then this is 3 meters long, so I get minus 300, because this is actually trying to get me to go that direction, because it's pointing downward, because it's a minus 300. So I get 700 minus 900 gives me negative 200 Newton meters, which means it's actually going this direction. Now if I look at F, do what?
So the 5 plus the 200, that's where you get the 7?
Yep, 5 plus 200.
What about, why do you only have 900 and half? What happens to the other 200?
This 200? If I do 200 times 0, I get 0.
Why times 0, another one times 3?
The distance.
Because this is A over here, and so at A, that's 0, and this is 3 meters to the 300,
All right, that makes sense.
okay? So now if I do F, F is loaded this way. I've got my 300 and my 200, so there's my 300, there's my 200. This is still 3 meters, and I have 400 going that direction. So now I would do my sum of my moments at A. There's my A. I end up with 400 positive Newton meters minus 3 times 200, that's Newton meters. So this becomes 400 Newton meters minus 600 Newton meters gives me negative 200 Newton meters, which means it's going that direction. And the loading on the top is both 500. So my sum of my forces is both 500. So F is the one that's the same. And if you want to play with them, just so that we can get more practice, we can do a couple more. Let's do G. Let's go ahead and look at G, because G was the first one you thought, right?
Yeah, just because it looks like.
Okay, G is the first one we thought. So let's look at G. So this is 1,000 Newton meters. This is 400 Newton meters. This is 200 going up, and this is 500 going down. no, 800 going down, sorry. 800 going down, 300, I can't even look at it today, I don't have my readers on and the red is hard to read. So that's what I've got, and this is at B. So if I do it around A, my force is 800 plus 300, so I got my negative 500, so I'm okay on my forces. So the forces are the same. But now let's do the sum of the moments about A. So the sum of moments about A are 1,000 Newton meters plus 400 Newton meters, because they're both going the same direction, they're additive. And if I do my 800, so I do my 800 and it's at A, so that's 0, and now I get my plus 300 at 3, because that's going up, it's causing it to go up. So I get 1,400 plus 900, this is all Newton meters, this gives me 2,300 Newton meters.
That's pretty good, isn't it?
Now, these problems are problem 3.01 and 3.102, and I think you've got several of them that are very similar coming in on a couple of these.
So, Ms. Winbach, on the part where it's 800 times 0, plus 300 times 3, could you explain that
Okay.
one more time right quick?
Okay, this is, so if I'm doing a torque, I've got to know my distances, right?
Yeah.
And if I'm doing it about A, what's my distance for A? A is right here. So what's my distance?
It's 0.
0, that's where that's coming from. This is 800 newtons, that's in meters. This is my newtons, this is in meters. This side over here, the distance was 3 meters.
Well, the distance they give you is like in the middle though.
The distance, no, what they gave you, this is drawing the picture, okay? And that's unfortunately, because you guys didn't have the lovely part of doing, because we cut out in school, we cut out drafting. What they've done is they've given you a line and they've said that this is 3 meters. Meaning the length of my bar is 3 meters. That's one of the things that when we're doing these problems, that's why I kind of wanted to show you through the picture. Because this is what they give you in this picture and here, okay, so going from here to here. So the distance between these two forces is 1.6 meters. That's where they get this distance here. The distance from here to here is 1.6 plus 1.2 to give me my 2.8. Because of how they drew the picture,
Yep.
okay? And so the whole beam is 4.8.
All right.
Yeah.
So, in that specific picture, then for A, then it would be 1.6 then, or?
Well, for A, if I were doing this around A, I would do the 1.6 times my minus 600. I'd do the 2.8 times my 100. And I would do my 4.8 times my minus 250.
Could you just do 4.8 times all those combined?
Yeah.
It depends, if I'm doing my equivalent loading, and that's where I'm at, I may or may not be able to.
And is it the reason that you multiply by those like 2.8 times 100, I think that is?
Uh-huh.
Is it because that's where it ends up stretching to?
That's where it ends up stretching to. That's my distance and that's my force. So this is my R and that's my force.
You need to go show this to some of the people that load lime at the quarries, because they'll load your truck heavy on one side and get up in the air, and you're like,
Well, and we'll actually do a couple of those problems. We bought 10 bags of Quikrete, and the guy says, "Where do you want it on your trailer?" And there's a reason we want it right over the wheels.
yeah, they've loaded heavy on one side of that end dump, and you go up in the air,
Yeah.
and they'll just start.
Yep, it'll start tipping you over. Exactly. But we'll actually do a trailer loading. Now, you guys should have everything you need to do these last set of homework problems. We've covered all of those.
Okay. Thank you.
You're welcome.
Should have been a cowboy. Should have learned to rope and ride.
kind of static torque in here?
Yeah,
Okay.
it's
It got
the,
charged to my thing, but I haven't picked it up right.
well, I'll show you where to get it. Hang on, let me turn this off, show you.
How'd your interview go, Ben?
I think it went pretty good.
Okay, so if I go in here, Ben, you go, we got my screen, let me go up here.